So it has been about 2.5 weeks since I prepared the alum solution in lab, and unfortunately I have no crystals yet. As you can see, the solution is clear and there are no signs that the crystals are starting to form. There are many reasons why my crystals couldn't have started to grow yet. Some of these reasons might include 1, contamination, which just means that the dust or something in the air from my room might have gotten into the solution. Another possibility might be that there hasn't been enough evaporation. We know that the alum crystals will appear when the concentration of the alum is higher than the concentration of the solvent, and this occurs as the solvent evaporates from the solution. Since I have no crystals yet, I know that the concentration of the solvent is still higher than the concentration of the alum. So there are 3 things that might affect this rate of evaporation, and one could be the temperature of the room. My room has been very cold lately, and if the room is too cold, then the solvent would be evaporating very slowly, and so this won't allow the alum crystals to grow since the solvent concentration is higher than the solute, which is the exact opposite of what we need to see these alum crystals. Another thing might be that there is just too much solution in my vial. If there is too much solution, then the evaporation rate would decrease. I have talked to other people in my chem class about their crystals, and the people who do have crystals have a lot less solution in their vial than I do in mine. And according to Orange County Marine Institute, this is because putting less solution in a vial will increase the interchange that the solution can have with the air and the atmospheric pressure. If I were to have less solution in a vial, I would increase the rate of evaporation, which would in turn decrease the concentration of the solvent, and this would then increase the concentration of the alum, which would form the alum crystals that we want. But I have the exact opposite, so that is perhaps a reason why I am not seeing crystals yet. For the calculations, we wanted to find the percent yield of the alum that we got from our experiment. To determine percent yield, we need to know the amount of all reactants used, the amount of product formed, and the balanced chemical equation, all of which you can see worked out here. Next, we need to find the amount of moles of reactants, which include aluminum, potassium hydroxide, and sulfuric acid. For aluminum, we divide the mass of aluminum foil by the molar mass of aluminum, and we get 0.0371 moles. For KOH, we have molarity, and so we use the 50 mils of the certain molarity, and we multiply the molarity by the volume. So what we get is 4 moles per liter times 0.05 liters, which gives us 0.2 moles KOH. The same goes for sulfuric acid. We multiply 9 moles per liter by 0.025 liters and get 0.225 moles of sulfuric acid. Next, we need to figure out how much product was formed, and this was weighed in lab. So the mass of our final product, which we obtained, was 15.49 grams of alum. Next, we have to establish a limiting reagent, and we see that that's aluminum, since when aluminum is completely consumed, the reaction cannot continue, and Next, we have to convert moles of aluminum to moles of alum by using stoichiometric coefficients. As we can see, we multiply 0.03137 moles of aluminum by 2 moles of alum over 2 moles of aluminum, which gives us 0.0371 moles of alum. Next, we convert moles of alum to grams of alum by multiplying by the molar mass of alum and making sure to take into account all the different elements that make up that alum. And as you can see how I multiplied the different masses and coefficients and ended up getting a molar mass of 473.388 grams per mole of alum. Finally, we multiply 0.0371 moles of alum by the molar mass and end up getting 17.56 grams of alum. This is our theoretical yield. Finally, we determine the percent yield by dividing the actual yield by, which was 15.49 grams, by 17.56 grams of alum, and then multiplying that by 100%. We end up getting a percent yield of 88.2%. This makes sense since it tells us that not a lot of alum got lost in the process. We could have lost some alum when filtrating the solution, and perhaps we let some stay behind in the beaker, or we could have also lost some when we were taking the alum from the filter and measuring its mass.